Hello, good morning. Here we are yet again for another lovely session, and the final session, or the final day anyway, of MENG 3310 Fluid Mechanics. So I have a two-part lecture that I wish to record today. The first I'm going to record in class right now, and then the second I'm going to record later in my office. But anyway, this is the final day for fluid mechanics, and what you're watching right now is the is the second to last recording in the series. Okay. So I have one last topic for this course. We have finished discussing major and minor losses. We've finished discussing the Darcy-Weisbach equation, etc. And today I want to look at the final miscellaneous topic for the course, and that is drag, boundary forces, and lift, or boundary surfaces, boundary layers, and lift. Okay, so a few objectives for this first lecture here. One, I wish to differentiate lift from drag. Two, determine a method to calculate drag, the drag force on a plate, and three, to calculate the drag force on a plate. So we're going to be getting into some boundary layer effects. All right, let us look at friction drag first. Let us consider friction drag. Okay, let's see. So let us consider a generic shape, although I'm going to draw a generic aerofoil. So consider a generic airfoil, like the kind of shape you'd use to make a wing or something like that nature, or a spoiler for flipped around the other direction. And basically, this is going to be an aerofoil that is moving through air, or air is moving past it, one or the other. From the point of view of surface-fluid interactions, those are really indistinguishable. Now, we only have two interactions at the boundary. There are really only two interactions. Only two interactions at fluid boundary slash interface, or fluid slash body interface. At fluid slash body interface, we have two different forces that can occur. And first is going to be shear stress. So wall shear stress, one. Oh, I wanted to do that in red. The first would be wall shear stress. So you may have some sort of shear stress between the fluid and the walls, between the fluid and the surface here. And this is a shear stress. It's a sliding stress. It's the frictional force of the fluid flowing past the object. That's the first potential force. And the second is going to be pressure, or normal force. So the second is going to be pressure, which again acts, by definition, pressure is going to act normal to the surface, or perpendicular to the surface. Acts perpendicular to surface. So we have a series of pressure arrows here, all acting perpendicular to the surface and distributed according to some sort of function that you could model if you wished, etc. And the sum of these, the integral sum of each of these, add up to two things. These sum up to a net force, and for an aerofoil or a body moving through air or any other fluid really, we say that these combine together into two different forces. We have two different forces, and we will say that the net force of these, and we'll classify the net force according to the direction of the resultant. So in particular, we'll say that they combine together to produce two things. One, lift, which is an upward force, and two, which is drag, which is a lateral force. And that would be opposite the direction of motion if the aerofoil was going forward into the fluid. Okay. So let us consider this now. Let us look at how we would calculate this. Well, drag would be the integral of p cosine theta dA. So again, drag is both of these are going to have a combination of both of the lift and the drag are going to be made from a combination of the wall shear stress and the pressure forces. So this would be the integral of P cosine theta, where theta is the angle between the body and the force at that point, or the fluid velocity at that point. P cosine theta dA plus the integral of so tau W, the shear, basically the shear stress, times, it's a W here, subscript, times sine theta dA, times sine theta dA. And again, where theta here is the angle between a surface normal vector and flow direction at that point. Between the surface normal vector and the flow vector and the flow direction at a point. So this is how you would describe the drag force in terms of both the pressure and the shear stress. And then the lift would be kind of the opposite. It'd be the integral of P sine theta dA, P sine theta dA plus the integral of tau W cosine theta dA. Cosine theta dA. And so again, both of these combine a pressure component and a friction component. So this is going to be your pressure component. Pressure component. And these would be your friction component here. Your friction component here. This would be your friction component. However, one of these terms is effectively zero. We're looking at shear stress here, and if we look at this component here, this one here is typically insignificant. This one here is typically insignificant. Just the way this works out, typically, this is due to shear stress again, so typically that will not generate, the shear stress will not generate substantial lifting force. Okay, so again, the idea here is that we're going to tally up all the pressure and friction and integrate over the surface of an object. So in other words, if we know the pressure and shear distribution, we can across the body or across the face of an object, we'll be able to integrate and find the overall drag and lift. However, this is tough. To actually work through surface integrals, especially for any kind of complex shape, is very, very difficult, and we tend to rely on other tools if we can have them. So let us look at, let us look at something a little bit simpler, the friction drag along a plate. Along a plate. Or we say a flat plate to be clear. All right, so let us consider a flat plate. Let's consider a flat plate here. And we'll look at this. And the basic idea is that as air flows along a plate, it goes from laminar to turbulent. Here. So if you have a flat plate, depending along the length of the plate, initially you're going to have kind of a distribution or a zone of disturbance like this. So if the flow is coming like this, right here it's going to the flow is going to start interacting with the plate, and it's going to be something kind of like, you're going to have something kind of like this here. You're going to have a behavior kind of like this, where you have both a turbulent and a laminar zone. So initially you get a velocity profile that's like this. Again, the velocity will always be zero right at the plate, but this is your laminar boundary layer. your laminar boundary layer. So initially everything, when the fluid first strikes the plate, it will be laminar. And then past a certain point, there will be a transition zone. Past a certain point, there'll be a transition zone. And then beyond that, it will be in a turbulent, you'll have a turbulent boundary layer. Beyond that, you'll have a turbulent boundary layer. Like this here, and we can discuss this more in some detail. A turbulent boundary layer. So what we're going to start with in the first interaction will be in a laminar zone. Then it will go through a transition, and then we'll have turbulent boundary flow. Or turbulent, turbulent boundary flow. Here. All right, so just a very basic idea of how these line up. Okay, so let us consider this. And this is where we really get into the difference between pipe flow and boundary flow. One major difference is that the Reynolds number is going to be different, and we actually don't have a constant Reynolds number along the length of the plate here. So with a pipe, you had pretty much a constant Reynolds number as long as the velocity was constant, right? Well, what is different about this is that the volume doesn't need to be conserved. This can the boundary can expand outward as it goes downward, and this can result in a change in or in other words, we can have change in the Reynolds number as we go along the plate. So the Reynolds number, it actually becomes a function of x. The Reynolds number can actually be something like this. It can be something to the effect of, something like this. This may not be the exact form, but something like this. The Reynolds number is equal to Vx divided by nu, where this would be, V would be the velocity, x would be the position along the plate, and nu would be the viscosity, the kinematic viscosity. So unlike the pipe, unlike all the previous pipe problems we've looked at, in all the previous pipe problems, again, the Reynolds number was constant along the pipe, as long as the velocity was constant, as the diameter is constant, etc. But in this case, the Reynolds number is actually a function of x along the length of a flat plate. So let's consider this. Now, if I look at the laminar boundary layer, and I'm going to have boundary values for Reynolds numbers that are a little bit different. So the Reynolds number limits that we've been looking at previously have been primarily related to pipe flow, but with boundary layer, different types of Reynolds numbers, different values of Reynolds numbers can give the characteristic of whether it's laminar or turbulent. So we need different boundaries actually. So in laminar boundary flow, so let's look at that laminar boundary region. So again, initially, what's happening here fundamentally is when the fluid first hits the plate, it has to start out as laminar, and because it hasn't had the distance or the time in order to translate into a turbulent condition. So we're going to have something that we call CO, which is going to be the, actually I should call this CD, sorry. CD, the drag coefficient, and this is something we'll be using throughout our analysis here. This is going to be the coefficient of drag, or the drag coefficient. And this is going to be equal to 1.33 divided by Reynolds number to the 1/2. Reynolds number to the 1/2, where since Reynolds number is a function of x, we use here that the Reynolds number for x equals L. So drag coefficient calculated, you calculate your drag coefficient based off of an x value equal to the length of the plate. Equal to the length of the plate. Okay. And the Reynolds number here, the limit for this, in order to tell whether a particular plate should be analyzed as either laminar or turbulent, I would look at the Reynolds number, where x equals L, and again, using the equation VL divided by mu, VL divided by mu here. And you can use, either, actually V or mu. I'd have to look at that. It's one or the other. But anyway, let's consider this. VL divided by mu. And here, let's see. Actually, I should probably use nu here, not mu. We should probably use nu here. That would make sense with kinematic viscosity. That would make sense with our units here. Then here, VL divided by nu, and this must be less than 5 times 10 to the 5th. 5 times 10 to the 5th. And so again, to determine whether you're going to be in one or the other, if you're analyzing a plate and want to find the drag on it, first you find out whether you're in the laminar region or the turbulent region, and we'll see how to calculate that in a second. Then next, you calculate whether you are your Reynolds number here, and then if you are in the laminar region, there'll be one equation for your drag coefficient, and if you are in the turbulent, there'll be a different equation. Okay, so then for the turbulent boundary layer, again, it's the same Reynolds number, and it's going to be that Reynolds number, again, at x equals L, evaluated at x equals L, is equal to VL divided by nu, and this needs to be greater than 10 to the 6th. Greater than 10 to the 6th. Now, so again, it's important to remember that the Reynolds numbers that will define turbulent versus laminar will be different for pipes and plates. So these are the characteristic Reynolds numbers are going to be different depending on what kind of system you're looking at. Now, the obvious question becomes what? If you looked at the limit here, it was 5 times 10 to the 5th, and this is 10 to the 6th. So what is the obvious question that raises? How do you handle the transition region? Obviously, how do you calculate the drag if you're in the transition region? Because the drag equation for this, the coefficient of drag CD, is going to be equal to approximately, for in the turbulent region, it's going to be equal to 0.031 divided by the Reynolds number to the 1/7 power. Isn't that lovely? The 7th root of the Reynolds number. So anyway, what we can see in the turbulent zone is that the Reynolds number is a function of both the the drag coefficient is going to be a function of both the Reynolds number and actually, let me label this a little bit better. This is for smooth pipe, for a smooth plate. And you'll need to use for a non-smooth plate, you'll need to use a different analysis tool. So if you have a non-smooth plate, it is a function of both the Reynolds number at x equals L and a function of epsilon over L. And you'll have to look up in a table or use a diagram of some sort to calculate this. For a smooth plate, it's fairly straightforward. There's a simple formula you can calculate, but you need to use some more tables, charts, and equations for the case of a non-smooth plate. So it gets a little bit more involved. Okay. So again, as I mentioned, the potential issue is what if you are in the transition zone? What if you are somewhere between where you're greater than 5 times 10 to the 5th, but less than 10 to the 6th? Well, I would go back to my good old-fashioned, escape clause in engineering. If I'm in a transition zone and I don't know where else to go, what is my universal backup?
Round up.
We could round up. We could round more conservative. That would be a certain way to do it. Or if you wanted to actually try to predict, you could always interpolate. So if someone put a gun to my head and made me predict the drag coefficient for a flat plate at 7 times 10 to the 5th, I would go and find the value at 5 times 10 to the 5th, the value at 10 to the 6th, and then interpolate between the two. That would be one way you could do it. Wouldn't be exactly perfect, but it would be useful to within a certain percent. Okay, so let us calculate friction drag. Calculating friction drag. Calculating friction drag. So let us find the process here. Let's look at the process. The first step will be to calculate the Reynolds number at x equals L. Reynolds number at x equals L, where x is the length of the plate, to find the drag coefficient. And as you may recall from physics class, or from some other class previously, the drag force is going to be equal to 1/2 times CD, the drag coefficient, times rho, the density of the fluid, times the velocity squared, times A. So again, let's go through these, where FD is the drag force. CD is the drag coefficient. Rho is the density of the fluid. Area A is the cross-sectional area, or the area of the flow contacts. And U, or V, are the velocity of fluid relative to the object. Some equations you use U, sometimes V, etc. Here, and then again, U or V are the velocity of fluid relative to the object. That is critical. Of fluid relative to object. So that is going to be very critical to some of our later analyses here. Relative to object, that is critical. So in other words, if you have a plane flying north, and if you have a plane flying north at 200 miles an hour, and the wind is blowing south at 100 miles an hour, I don't know why you would fly the plane into there, but let's say you did. If the plane was flying north at 100 miles per hour, or say 200 miles per hour, ground speed relative to the ground, and the wind is going south at 100 miles per hour, the speed that you would use for calculating drag and lift would be 300 miles per hour. It relates to, or we're talking not necessarily the speed of the object relative to the Earth or some other quote-unquote stationary reference point. We're talking about its velocity relative to the air around it, because ultimately that is what's going to generate lift and drag. Okay? Let's see. Opposite directions. Again, relative to each other. Relative to each other.
So they're always added?
No, I'm saying does that make sense? Did I add that up properly?
If it's flying at 200 miles an hour against the wind, relative to each other, it's flying only 100 miles an hour. Right?
Is it? Or is it 300? Let me, I need to think through my vectors here.
If it's flying
With the wind?
Let's see, that,
No, but you're calculating drag though. It's you add it. It's like when you do a car crash.
yeah, it's more like a car crash. Yeah, it's a relative, yeah, think of a car crash. That's a good example. Think of a car crash. If you have two cars that are going to collapse and they're going to strike each other and they're each going 40 miles per hour, the speed of impact, since they're going toward if they're going directly head on, is 80 miles per hour. That's what we're talking about here. It's the speed relative to one another. So, in other words, if your plane is going to, now again, what you're calculating there is with that 100 miles per hour, that would end up being the ground speed of the aircraft. So if the aircraft was trying to fly at 200 miles per hour, if it could only fly 200 miles per hour relative to the wind, and the wind was going 100 miles per hour south, it would actually end up traveling only 100 miles per hour. So I remember, have you ever seen a bird fly backwards?
Mm-hmm.
I have. It's actually kind of funny. Oh, it's sad in a way, but I grew up in Iowa, and we had. I grew up in a little small town, and it was kind of on the edge of some fields, and we would sometimes get big windstorms and stuff up there. And I remember one time I looked out the back window, and I saw a bird flying backwards. It wasn't that it was propelling itself backwards; it was flying forward relative to the air around it, swimming forward in the air. But the air was going backwards faster than it could propel itself forward. So even though it was moving just normal like a bird normally does, the poor bird was flying backwards. So that bird was having a bad day. But anyway.
That's not during Hurricane Rita.
Oh boy, yeah, that's it. So again, let me give it, and I do actually have a few examples of this. Let's look at some examples of calculating the relative velocity. And I'm going to distinguish this V maybe using, this is if object is stationary or if the fluid is stationary. I would use V if only one thing is moving. And maybe I'll use U for a relative velocity. So, or we could also say again, force drag is equal to 1/2 CD times rho U squared A. Now let us look at, I want to do some examples of the calculation of U. Examples of calculating relative velocity U. So let's consider this. First of all, what if the fluid is stagnant and the plate is moving? So, first example, if the fluid is stagnant, these are just basically going to be different examples or scenarios. Fluid stagnant, plate moves at velocity. Plate moves at, let's say, 30 feet per second, at V equals 30 feet per second. Well, this is easy. This is just U equals 30 feet per second. Very simple. Trivial. Okay, next scenario. What if the plate is still? Plate's still, but fluid. Fluid moves at 30 feet per second. At V equals 30 feet per second. Well, in this case, U would again be 30 feet per second. Here, if the plate moves, let's say the plate is moving, depending on direction, I suppose, at V equals 10 feet per second, and the fluid moves, let's say at, well actually these arrows will show direction. So the plate is going to move at 10 feet per second this way, and the fluid moves in the same direction at V equals 50 feet per second. Well here, U would be 40 feet per second. Because again, we're talking about the relative difference between them. And then 4, let's say the plate, or any object, moves at 10 feet per second this way. And then the fluid, or the wind, or whatever it is, and I'm going to use air as an example for a lot because I'm always thinking airplanes when I think of drag, but the same idea applies to hydrodynamics as well. So the same ideas of drag and lift can be applied to a watercraft, as they often are. And so we'll have a plate moving at 10 feet per second and to the right, and a fluid moving at 50 feet per second to the left. And this comes together to produce a relative velocity U equal 60 feet per second. So again, it is the relative velocity that we'll use when calculating drag. Now, in the second part of the lecture today that I'm going to record, we'll see that sometimes, well, let's see, well, I'm not sure if we'll get to it, but one interesting application of this is that sometimes there are problems that we have to be very careful of which U and V we use. So, for example, if I asked you to calculate the power that is required to overcome a drag force, we know that power is equal to what? Power, or if I was asking, remember P equals FV, remember that? Power equals force times velocity, right? And so, in that case, if I was asking you to calculate the power, I would use the relative velocity to calculate the force, but I would use, say, the ground speed to calculate that V for a plane flying through the air. So it wouldn't actually be the same. And that is one case where the V and the U would actually both need to be used independently. Okay, so I want to work through an example here of a flat plate. So let us say we have two different plates. Let us consider two different plates, both smooth and fixed. This is going to be plate 1, and then I'm going to have plate 2. One is a square, and the other one is a long rectangle. Here, and so this one, and so this is going to be plate 2. And let's say this is a 10 foot by 10 foot, a 10 foot by 10 foot flat plate, smooth fixed plate. So fixed just means it's fixed to the ground, it's not going to go flying anywhere. So all that I'm writing here is given. And the other one is a 5 by 20 foot. So these are both going to have, sorry, 5 by 20, not 5 by 10, sorry. 5 by 20 foot. Let me write this proper, 5 foot by 20 foot. So both of these plates are going to have the same area. And this is also a smooth fixed plate. And then I'm also given the following. I am told that the velocity of the air, so V of the air, is going to be 29.3 feet per second, oddly specific. And then the density is going to be 2.38 times 10 to the negative 3 slugs per cubic feet. Slugs per cubic feet, and the viscosity, nu, the kinematic viscosity, is 1.57 times 10 to the negative 4 feet squared per second. Square foot per second. And I want us to find the drag force for each of these. Find the drag force for each of these. So let's do that. So I'm going to find the drag force for each of these. Now, let's see. Now, what's interesting about this is that, what's interesting about this, at least in my mind, is, well, first the velocity is like this and like this. Now, what's interesting about this is, this sort of really gets to the heart of the difference between drag on a plate and drag you might have, say, on a, I don't know, a aircraft or a boat or something like that. Usually we think of drag in terms of cross-sectional area, right? Usually think of drag in terms of cross-sectional area, but this is actually drag along the plate. See, notice, what didn't I give you? What didn't I give you? I didn't give you the thickness of the plate. I did not give us the thickness of the plate. So since we see that, we obviously know that the thickness can't be important. And the reason for this is for objects that are plates, well, there would be a small amount of drag on the surface here, but the frictional drag, or the drag from the broad flat surface, is what's going to dominate. So usually think of drag in terms of cross-sectional or projected cross-sectional area, but for plates, it's actually the surface. The flat surface is going to generate the vast amount of the drag force. Everything else is really a rounding error. So let us calculate it first for plate 1 and then for plate 2. plate 1. The first step, of course, will be to calculate the Reynolds number. And the Reynolds number is going to be equal to Vx divided by mu. Now, we could use u if we wanted to, but it's not really going to matter here because, well, actually, I gotta back up. Another note here. Note, always use V. Always use fluid velocity. Well, let's think about this. Always use fluid velocity, yes. Well, no, I guess you're fine using, well, let me think about this. Let's see, I'm trying to think if I can come up with a better example of this. But, let's see. No, okay, I will just use, always use the fluid velocity V. No, I would think it would still, I think it's probably the relative velocity that would be more important. Relative velocity for calculating Reynolds number. I'm going to use a V here, but that's only because the plate is stationary. Velocity for calculating Reynolds number. So Vx divided by nu, this is going to be 29.3 feet per second. 29.3 feet per second times a length of 10 feet divided by our our kinematic viscosity of 1.57 times 10 to the negative 4 feet squared per second. And this comes to 1.87 times 10 to the 6th, 1.87 times 10 to the 6th, which will indeed be greater than 10 to the 6th. So yes, this is turbulent. So we can use our equations for turbulent flow. Then the drag coefficient is going to be equal to 0.031 divided by Reynolds number to the 1/7 power. And this is equal then to 0.031 divided by a Reynolds number of 1.87 times 10 to the 6th to the 1/7 power. And this is equal to 3.94 times 10 to the negative 3. 3.94 times 10 to the negative 3. And if you then work through the drag coefficient, or the calculation of drag force, I should say, equal to 1/2 CD rho u squared a. This is going to be equal to 20, that's going to be equal to 1/2 times 3.57 times 10 to the negative 3 times 2.38 times 10 to the negative 3. Huh? 3.94 here. Oh yes, the oh yeah, thank you. 3.94. Sorry. Or, did I write that down wrong? Let's see. 3.94. 3.94. Yes, sorry about that. Getting myself a little mixed up in my notes. Times 2.38 times 10 to the negative 3 slugs per cubic feet. Times the relative velocity of 29.3 feet per second squared. Times the A of 100 feet squared. And I get a drag force that is equal to, the drag force that will be equal to, simply that comes to 0.40 pounds. Or just 0.4 pounds, not 0.04. So 0.4 pounds. You know, the more I look at this, this is giving me trouble. I need to do some more research on this. I need to figure out for the Reynolds number where I can see arguments for both. So I need to just think about that one a bit more. I need to do some research on that. The equations I have show that you use V for the Reynolds number, not U, but I could see an argument for either one. So I need to do a little research on that and get back to you on that. So I'll try to put that in the second lesson. That's a question I need to do a little research on. Whether when you're calculating the Reynolds number for the flow, whether you use the relative velocity or the absolute velocity of the fluid with respect to itself, so or respect to ground. So I need to do a little more research there. So don't take that as gospel yet. But anyway, the equations I have listed here show show V, but I'm a little skeptical of that. I need to double check whether we use V or U on that. So give me a minute to, well, not right now, but I will research that before I record the second portion of this lecture. Plate 2, the Reynolds number is going to be, again, where x equals L. Now for this particular problem, it's not going to make any difference because the plate is stationary. I'm just wondering how we would handle a moving plate. That would be where it would be a bit more complicated. 29.3 times 20 feet divided by 1.57 times 10 to the negative 4. Same equations as before, feet squared per second. And this is equal to 3.73 times 10 to the 6th, which is indeed greater than 10 to the 6th, so it is still turbulent. And the CD, the drag coefficient, is 0.031 divided by the Reynolds number to the 1/7 power. And this is where my 3.57 was coming from earlier. This is 3.57 times 10 to the negative 3. 3.57 times 10 to the negative 3. And then the drag force, FD, is equal to 1/2 times 3.57 times 10 to the negative 3 times 2.38 times 10 to the negative 3 slugs per cubic feet times 29.3 foot per second squared, the relative velocity, times an area of 100 feet, 100 square feet. And this comes to 0.36 pounds. So the previous value was 0.40 pounds, and we see that the longer plate actually will have a slightly lower drag force, even though both of these plates have the exact same cross-sectional area. Okay, so I think that's, I'm going to let that do. I'm going to let that do it for today. I will record a second one for to make up for Friday later this afternoon, and that will do it. All right, and thank you.